Hi everyone! Welcome to part 4 of chapter 19. Today we're going to wrap up our talk on electrochemistry by covering electrolytic cells. Thus far we've talked about voltaic cells, which are spontaneous and generate electricity. In electrolytic cells, we actually input energy to cause those reactions to occur. So we're going to look at why we might want to, have those types of reactions and how we would calculate the cell potential in those instances. So in all cells, whether they're voltaic and spontaneous or electrolytic and non-spontaneous, oxidation is going to occur at the anode and reduction is going to occur at the cathode, so nothing changes there. In voltaic cells, those are spontaneous and they will generate electricity, and we can use that to do work. The anode is going to be the source of the electrons, and it has a negative charge. The cathode is going to pull those electrons towards it, and it has a positive charge. So this is different in electrolytic cells. Okay, in a voltaic cell, those electrons are kind of doing that on its own, essentially. And we have a voltmeter across the wire to measure how much current is being generated. While in an electrolytic cell, we are having to drive the reaction using an external electric current. So instead of a voltmeter, we will have a battery in its place. And so what the battery does, right, it causes the electrons to be drawn off of the anode. And they're going to be pulled off of the anode and attracted to the positive terminal of the battery. And then the electrons are going to be forced toward the cathode, right? So electrons are going to go toward the cathode from that negative terminal of the battery. So essentially the electrons are going to be going in the opposite direction. Okay, so let's look at this. So in a voltaic cell, we're showing our electrons going from left to right, just like they normally do. The electrons are going to leave the anode and they're going to travel to the cathode. And like I said, we're going to have a voltmeter there to measure the amount of current that's being generated in that process. But in an electrolytic cell, we're going to use a battery to push the electrons the opposite direction. Okay, so now instead of the electrons, going from left to right, they're now going from right to left. And as you can see, the anode and the cathode have switched places. So oxidation is still occurring at the anode and reduction is still occurring at the cathode, but now we've totally made this reaction backwards, essentially. So now our zinc is going to be reduced and our copper is going to be oxidized instead of the other way around in the voltaic cell. You'll notice the voltage source has to have a voltage greater than 1.10 volts to make it go the opposite way, right? Because that is the amount of electric current that we were generating in the voltaic cell. Okay, so we have to overcome that and then, to make it go in the reverse. So let's compare these real quick. So in a voltaic cell, we are always going to have a negative value of delta G. It's always going to be negative, it's spontaneous. And we're always going to have a positive value for the E of the cell because, again, it will be spontaneous. The oxidation will occur at the anode, the reduction will occur at the cathode, that's all the same. But the sign on our anode is going to be negative and the sign on our cathode is going to be positive. And the reason that I'm pointing that out is because it flips in the electrolytic cell. Our anode will now be positive because we are going to pull electrons off of the anode. And then we're going to force those electrons toward the cathode, which will make the cathode negative. So we flipped the signs on our electrodes. Otherwise, our electrolytic cells are going to have a positive value of delta G because they're non-spontaneous. They're going to have a negative value for E of the cell because, again, non-spontaneous. But oxidation is still going to occur at the anode. Reduction is still going to occur at the cathode. We've just changed the signs on those electrodes. All right, so electrolysis, right? Electrolytic cells, electrolysis, right? Electrolysis is the process of using electric current to drive a non-spontaneous reaction. So like we talked about last time with fuel cells, we were using the hydrogen and the oxygen to generate water. And that was a spontaneous process, right? We were doing this in a voltaic cell. We said it could be maybe used to power things in the future. But the opposite, right? What if we took water and instead we made it back into hydrogen and oxygen? Okay, so we're taking water apart and breaking it into its component elements. Okay, this would be electrolytic. right? We're, causing that process to go backwards. So we would need to input energy. So as you see, there's a battery here. We can input energy to split water back into oxygen and hydrogen, which is cool. So electrolysis carried out in an electrolytic cell. And like I said, electrolytic cells can be used to separate compounds or, molecules back into their elements. So in electrolysis, we use our electrical energy to overcome that energy barrier of a non-spontaneous reaction, which allows it to occur, right? So we can, if we have one that goes forward normally, like I was just talking about in a hydrogen fuel cell, we react hydrogen and oxygen to make water. That was a spontaneous process. But we can make it go backwards, right? If we just flip it, we can use water to make hydrogen and oxygen by inputting some energy, okay? The reason we might want to do this is to extract metals from minerals, to purify them, right? We would find a metal out, in the real world as its ore, and we could use electrolysis in order to separate that ore back into, say, iron and oxygen, or aluminum and oxygen, right? Whatever it was supposed to come from. So we can purify metals that way, which is neat. We can also produce hydrogen for fuel cells. Last time we were talking about the fact that fuel cells weren't going to be really useful yet because we don't have a good source of hydrogen. So we can use electrolysis to split water and get our hydrogen that way. Maybe not the most efficient way, but we can do that. And we can also use it for metal plating. So if you have a gold-plated ring or silver-plated jewelry, right, the way that we do this is we use electrolysis in order to plate it out. And we're going to talk about that a little bit later. So in electrolytic cells, the electrons are being drawn away from the anode, right? So it's connected to the positive terminal of that external power source. So we're pulling the electrons away from the anode, and then we're forcing them to the cathode. Okay, so that's going to be connected to the negative terminal of that power source. And again, the process that takes place is going to be the non-spontaneous process. So whenever you're calculating the E of the cell, just as like a double check, it should always be negative if you know you're calculating an electrolytic process. Okay, if it comes out positive, that's not electrolysis. That would be a voltaic cell. So in these, we're always going to have a negative value for our E of the cell. Okay, our electrical current is typically going to be supplied by a DC power supply. We can't use AC because that alternates the flow of electrons, so our reaction wouldn't be able to go. So we just need a DC power supply. Some electrolysis reactions require more voltage than our E of the cell predicts. Okay, so if we were to calculate, like that water, right, splitting water back into hydrogen and oxygen, we could, use our table of reduction potentials just like we've been doing so far, and we could calculate the E of the cell. Okay, but the E of the cell in electrolysis is not actually going to be what you calculated on paper. And so this is called overvoltage. Sometimes we need extra in order to make the reaction occur. This is typically, in this class, this is just going to be for water that we're going to calculate our overvoltage, and it's going to be our water on inert electrodes producing hydrogen or producing oxygen. And because these are both gases, there's this really large activation energy that's associated with forming that gas at the metal surface. And that's not being taken into account when we just simply flip the reaction backwards, right? Because before we were using the gases to produce water, and now we're instead using water to produce the gases. So it's not just a simple kind of flip it around. So what you'll do is you'll just add somewhere between 0.4 and 0.6. I usually just add 0.6 to err on the side of caution. But you'll add 0.6 to that voltage in order to account for this difference, okay? So that's what's called overvoltage. It's the extra voltage needed to drive the reaction, and again, it's usually because we're producing a gas at the metal surface. And this is important because if you don't take into account that overvoltage, you might incorrectly predict the products of an electrolysis reaction. And we're going to get into predicting the products in a little bit, so don't just blow this off. Make sure you take it, account for the overvoltage anytime you're dealing with the electrolysis of water. All right, electrolytic cells. So again, like I said, the source of our energy is going to be a battery. It could be a DC power supply, just not AC. The positive terminal is going to attach to the anode, and then the negative terminal is going to attach to the cathode. So our electrolyte, right, our solution essentially can be one of two things. It can be either an aqueous salt solution, right? So we've, made salt water or whatever the case may be, or you can use a molten ionic salt. So if we melt our salt, then there's no water, right? And so then we would just have our salt. So these are actually used for two different things. And then our cations, any cations, are going to attract to the cathode, because remember now the cathode is negatively charged. So our cations are going to be attracted to the cathode, and our anions will be attracted to the anode because it's positively charged. So cations are going to pick up the electrons off that negatively charged cathode and will be reduced. And the anions will release their electrons to the anode because it's positively charged, and they will become oxidized. So when you are doing electrolysis of pure compounds, okay, so this is not an aqueous solution, this is a pure compound. We are going to melt it and we're going to make it a liquid state. No water though. Our electrodes are typically going to be graphite. Our cations, like I said, are going to be reduced at the cathode to the metal element. So if you had like Ca+, now you would have Ca solid. And your anions are going to be oxidized at the anode to your nonmetal element. So say you had, Cl-, you would now have Cl2. Okay. So here's an example. This is what we were talking about earlier. This is the electrolysis of water. So our water at the anode, right, we are going to have oxidation occurring. So our oxygen is going to be oxidized to O2 gas. And at the cathode, our hydrogen will be reduced to hydrogen gas. Okay, so again, oxidation still occurring at the anode, reduction still occurring at the cathode. The only thing that's different is going to be the charges on those electrodes. Right now, our anode is positively charged and our cathode is negatively charged. Here's what it looks like for sodium chloride. Again, we don't have any water here, right? The last one was water, but here we don't have any water. This is just melted sodium chloride. So you can imagine this is taking place at very high temperatures. And so what's happening, right, is we are having oxidation occurring at the anode, right, and then reduction occurring at the cathode. So our chlorine is being changed into Cl2, right, and then we have sodium being changed into sodium solid, okay. Also, I see a typo here. This should not have a negative sign. There you go. But we're using our, we're turning our anions into their elements and our cations into their elements. Okay, so we're taking our molecule, we're taking our compound and turning it back into its elements using electrolysis. So sometimes though, it's not as straightforward as, as this one, right? Where your anion is being oxidized at the anode and your cation is being reduced at the cathode. It's not always that straightforward because sometimes you may have a mixture. And so if you have more than one cation present, the cation that's easiest to reduce will be reduced first at the cathode. So this will have either the least negative, right? Because a lot of times we're dealing with negative values since this is electrolysis. So it'll be the least negative or most positive E reduction, right? Same as normal when we're trying to pick, which one gets reduced or which one gets oxidized. The one with the most positive or least negative reduction potential will be the one that is reduced, okay? The reason for this is that the stronger oxidizing agent is more electronegative, so it's going to gain those electrons easier, right? Think about, so if we have some kind of metal, right? If it's more electronegative, it's going to be easier to attract those electrons, so it will be easier to reduce, which means it's the stronger oxidizing agent. Okay. If we have, same thing, more than one anion, the anion that's easiest to oxidize will be oxidized first at the anode. So again, you would change your reduction potentials into your oxidation potentials and then figure out whichever one is the most positive or least negative. And so again, you're going to have the stronger reducing agent be the one that's less electronegative because it's going to lose electrons easier, right? It will be more easily oxidized if it's not so electronegative and holding onto those electrons really tightly. So let's go through this. Predict the half reaction occurring at the anode and the cathode for the electrolysis of a mixture of molten aluminum bromide and molten magnesium bromide. So you see both of those are liquids because this is molten, not aqueous, right? There's no water here. So when we're looking at this, the anion is going to be oxidized the cation is going to be reduced. That's what we've been talking about. Both of these have the same anion, so bromine wins. It's going to be the one that's oxidized. But between the two cations, we need to figure out which one of those will be reduced. Okay, so we have our options are aluminum, gaining 3 electrons and becoming, aluminum solid, and magnesium gaining 2 electrons and becoming magnesium solid. So the way we figure out which one will occur is we're just going to look at their reduction potentials. So if we look at the reduction potentials, both are negative, right? Because these are metals. They like to lose electrons. So to gain them, is a negative value because it's usually not what they do. So we're going to take the one that is the least negative, right? The most positive, right? The least negative here is aluminum, so it's the easiest to reduce, and therefore that's the reaction will occur. Aluminum is going to be the stronger oxidizing agent because aluminum is more electronegative than, magnesium, so aluminum gains electrons easier than magnesium does. So our oxidation is going to occur at the anode, our reduction is going to occur at the cathode. So we have the anode equation there. There was only one to choose from. We only have one anion. And then the cathode here is going to be the one that's the easiest to reduce, and that would be our aluminum because it has the least negative value. All right, you try one now. So this says predict the half reaction occurring at the anode and the cathode for the electrolysis of a mixture of molten magnesium chloride and magnesium bromide. So go ahead, pause here, try this out, and unpause when you're ready to see the answers. All right, let's go through this. So again, anion's going to be oxidized, cation's going to be reduced. Both of these have magnesium, so that's the one that's going to be reduced. But we have chlorine and bromine for our options for oxidation. So we need to look up their reduction potentials. Okay, and again, when you look up their reduction potentials, you need to flip it because now we are oxidizing these two elements. So when we look at them, we see that bromine has, a less negative E0 value. Therefore, it's going to be easier to oxidize than it's going to occur. And this makes sense, right? Bromine is going to be the stronger reducing agent because bromine is less electronegative than chlorine. And since it's less electronegative, it's going to lose those electrons easier. Okay. Oxidation is going to occur at the anode. Reduction is going to occur at the cathode. So we can just write those reactions down. Okay, so now those were molten solutions. Those were when we melted our salts. There was no water there. But if there is water, then water, like we saw, water can also be oxidized and reduced, right? Before we were, splitting water into hydrogen and oxygen because there were, one was reduction, one was oxidation, right? We get those two gases out. So not only can you reduce your cation to a metal, you can reduce your water to H2. And not only can you oxidize your anion to an element, you can also oxidize your water to O2, okay? So we are going to have to also factor those in. So kind of like in the last problem when we were like, we could either oxidize this one or that one, right? You can, reduce your cation or you can reduce your water. You can oxidize your anion or you can oxidize your water, okay? So you'll compare those to the reduction potentials for your elements and see which one will occur. Sometimes you can also oxidize your anode. Your electrode. This is kind of unusual. The reason is, a lot of times we'll use graphite, but if you're using copper, you might also accidentally oxidize your electrode, and you'll have to take that into account. Again, typically we don't use that because it's a competing reaction, but just if you ever see it, take it into account. Whenever we're doing this, the half reactions that lead to the least negative cell value will occur. Okay, just like normal, you're going to pick the one that's the least negative or the most positive. Pay attention though. Overvoltage can change those conditions. Remember, for things like water, so this value, let's talk about this. This value is the one that's in your book. Okay, and same here. If you just flip them around, then you'll get those values. But a lot of times we are doing these reactions at pH 7, right, at neutral conditions. And at when our solution is neutral, our concentration of H plus is not 1 molar. Okay, a lot of times I think people would see pH 7 and they're like, that sounds like a standard condition, but it's not, because our hydrogen ion concentration is not 1 molar. Our hydrogen ion concentration, right, is 1 times 10 to the minus 7. So we have a different value here, so you're going to want to write these down. When you're doing reactions that are at pH 7, these are the ones that you will use, not the ones from the back of your book. Okay, so that's the first issue, is that a lot of times we're doing these reactions at pH 7. The other issue is that, like I said before, we're producing a gas in each one of these. We're producing hydrogen, we're producing oxygen, and these values aren't taking that into account because they're just the negative of what would normally happen when we use those gases to produce water. So both of these times, you're just going to add a negative 6, right? A negative 0.6 volts to each one of these so that you can get the actual value, or at least closer to the actual value of what we would need. So this E value, and not E naught, right? But E value would be closer to, like negative 1.0 volts. And then this E value would be closer to negative 1.4 volts. So you need to take those over voltages into account. Otherwise, you might accidentally get the wrong products in these electrolysis reactions. Okay. So let's go ahead and see how this plays out. So if we had the electrolysis of sodium iodide, so we have two possible reactions that can happen for our oxidation. We can oxidize our anion, right, and we can get I2, or we can oxidize our water. Okay, so this is similar to what we were doing before when we had two different ionic compounds and we were trying to figure out which one of those would be oxidized or reduced. Same kind of thing, except now our competing reaction is water instead of some other metal, okay, or some other nonmetal. So here we have two possible oxidations. We can oxidize our iodide or we can oxidize our water. So we're always going to go with the one that is less negative. So that will be this value. Okay, so our iodide will be oxidized. And then if we look at our reductions, right, reducing our sodium is a really big negative value. And then reducing our water was, a smaller negative value. So our water will be the one that is reduced. Okay, so again, remember, you need to take into account these over voltages. Here, it didn't make a difference because there was such a large difference between these values, but sometimes it will. So make sure you're always taking into account the over voltage. So if we look, our overall reaction then, we are going to oxidize our iodine and reduce our water. So nothing happens to the sodium. Okay, we would need a lot more electricity going through this in order to reduce our sodium. Okay, so iodide is going to be oxidized, water is going to be reduced, and we'll produce I2, some hydrogen gas, and some hydroxide. So let's try one. So this says, predict the half reaction occurring at the anode and the cathode for the electrolysis of lithium iodide, which is aqueous. So that means there is water present. So make sure you're looking at that. If that was an L, a liquid, that means it's molten and we don't have water competing with our lithium and our iodide. But when we have an aqueous, that means there is water present and the water can be oxidized and the water can be reduced. So let's go through this. So we have two possible oxidation reactions. We could oxidize our iodide or we could oxidize our water. We could reduce our lithium or we could reduce our water. So we need to look up all of the reduction potentials for all of that. Okay, so if we look at iodide, right, we have negative 0.54 volts, and our water would be negative 1.4 when we're taking into account that over voltage, right? So that means our iodide will be our iodide will be oxidized, just like we were looking at in the last problem. And then our lithium has a really negative value for our E value, right? It does not want to be reduced whatsoever. So water here will be reduced. And again, remember, the reason that lithium's not, able to be reduced very well is it's because it's not electronegative. It's not going to attract that electron. That's why that E naught value is so big, or such a large negative number. Okay, so now we have our iodide being oxidized, our waters being reduced. We can combine those together and figure out which one happens at each reaction, or at each electrode. All right, your turn. So go ahead and try the same process, but now we have aqueous sodium bromide. So again, it's aqueous, we have water competing here. Go ahead, pause here, see if you can figure out which reaction is going to occur at the anode and the cathode for this reaction. All right, let's go through this. So again, we have two options at each electrode. We can have the bromide being oxidized, or we can have the water being oxidized, and we can have the sodium being reduced or the water being reduced. Okay, so if we go ahead and look at those, then we will get that our oxidation, right, if you didn't take into account, so this is, if you got this wrong, here's where it was. If you didn't take into account the overvoltage here, right, and you looked just at this value versus this value, you would see water having a less negative potential, right? It would be more likely to be oxidized than bromide if you didn't take into account the overvoltage, and you would get this wrong. But, right, we have to take into account the overvoltage, therefore bromide is the one being oxidized. And then water is the one being reduced because, like we talked about before, sodium really doesn't want to gain that electron. So again, we can just copy those down. So we have our anode reaction is our bromide oxidation, and then our cathode reaction is our water reduction. All right, on to the next topic, electroplating. So we can use these electrolysis reactions in order to plate a metal onto an object, which is really cool. So when we're doing this electroplating, the object that's going to be plated needs to occur at the cathode. Okay, so the cathode is going to have these electrons that are being, sent to it essentially, which makes the cathode negative here. And all of our metals are going to be aqueous in solution, and they're going to be positively charged. And so those positively charged metals are attracted to the negatively charged cathode, and they will just plate onto the outside of whatever is there. This whole thing is going to end up being negatively charged, so it just attracts the metal right onto it. It's really cool. Yep, that's all I had to say about that. So we can actually calculate how quickly our metal can be plated out, or how much metal can be plated out if we know the current. Okay, so in an electrolytic cell, the amount of product made is related to the number of electrons that are being transferred. We can think of the electrons essentially as a reactant in this process. And so the number of moles of electrons that flow through this electrolytic cell are going to be dependent on the current, right? How much electricity are we sending through? And the length of time. How long are we letting this thing run? Okay, so a couple things we need to know. 1 amp, which we've talked about before, is 1 coulomb of charge per second. So 1A essentially is equal to 1 coulomb per second. And 1 mole of electrons is equal to 96,485 coulombs of charge. And we talked about this before. That's Faraday's constant. So we can use both of these two pieces as conversion factors in essentially a stoichiometry kind of process. So I'll show you how to work this out. So this says calculate the mass of gold that can be plated in 25 minutes using 5.5 amps for the half reaction, right? So we're going to plate something in gold, and we want to know how much gold we can plate out under these conditions. Okay, so we know a bunch of things. First though, so we have minutes and we have amps. So remember, amps is coulombs per second. So if we use our minutes and we convert it to seconds, right, and then we can use our coulombs to go ahead and our amps to convert our seconds into coulombs, and we can go from there. So let's start off looking at that. So we have 25 minutes, and we know that for every 1 minute there's 60 seconds, so we can convert minutes into seconds. And then we can use our amps, like I said, as a conversion factor to convert seconds into coulombs. So now we have a way from getting to time to charge. And then, if you'll recall from the last slide, we know Faraday's constant. Okay, for every 96,485 coulombs of charge, that will equate to 1 mole of electrons. So now we can change our charge into moles of electrons, which is something useful, right? And we see in this reaction, we have 3 electrons that are being used. For every 3 electrons, we're going to plate out 1 mole of gold. okay? So for every 3 electrons, we can plate out 1 mole of gold, and then we can use the molar mass of gold to convert our moles of gold into grams of gold and calculate that there. Okay, so these problems, when you see this, it's just a lot of conversions, and it's nothing hard really. You just need to know, like I said, that amps are coulombs per second, and you need to remember Faraday's constant is coulombs per mole of electron. But otherwise, it's really just manipulating units until you get your answer. So let's go ahead and have you try one. So this says calculate the amperage required to plate 2.5 grams of gold in 1 hour. So you're calculating amps. You're calculating coulombs per second. And so just to help you out here, right, you're going to need to calculate, change your time into seconds, change your grams into coulombs, and then you can find your amps. So go ahead, pause here, see if you can try it out, and come back when you're ready to see the answer. All right, let's go over this. So we have 2.5 grams of gold, and it's going to be in 1 hour. Okay, so I'm going to go ahead and convert both of these in the same train track, in the same kind of conversion problem. You could do it separately and then divide them up at the end. Either way is fine, you'll get the same answer. So we have our 2.5 grams of gold, and so we can convert our grams of gold into moles of gold. And then we can use, right, for every 1 mole of gold, we're going to need 3 moles of electrons. Okay, so this is kind of going backwards from what we did last time. And then we can use Faraday's constant, and we can change our moles of electrons into coulombs. Okay, so that's there. And then now we have coulombs, which is part of what we needed, right? And so now we'll just change our hours into seconds. So for every 1 hour, we have 60 minutes. And then for every 1 minute, we have 60 seconds. Okay, and so now we're left with coulombs per second, which is amps, which is what we were trying to find. Cool. All right, let's talk a little bit about corrosion. This is our last topic in this chapter. So corrosion is a redox reaction, and it's not an electrolytic process like we've just talked about before. It's spontaneous, right? If you leave things out in the rain, they're going to rust. They're going to corrode. So it's the undesirable, spontaneous, gradual oxidation of a metal by an oxidizing agent in the environment. And this is usually because of oxygen gas. Okay, so the metal has to be reduced, right? We talked about this earlier, in order to extract it from its ore. When we find our metal just kind of out in the world, it's not going to sit there as, aluminum or iron, right? It's iron 3 oxide or aluminum oxide or whatever the case may be. And we can use electrolysis in order to get the metal as just iron or just aluminum, right? We've been talking about that. We can purify our metals using an electrolytic cell. But if we leave it out, then it's going to undergo that spontaneous oxidation back to its natural state. Essentially, it's going to kind of turn back into its ore. Maybe not exactly, but something closer to that. And since many metals that we use are active metals, this corrosion is like a really big problem. The reason that we use metals a lot of times is they're really strong and they're really malleable. But if you turn them into an ionic compound, right, if you turn them into an oxide, now they become very brittle. And so they're no longer very strong, they're no longer very malleable, right? And they lose a lot of those properties that we wanted from the metal in the first place, okay? And a lot of times when our metal undergoes corrosion, the product that is made, it doesn't stick to the metal anymore, and it just kind of flakes off, right? If you've seen like something rust, sometimes you can actually scrape the rust off, whereas you couldn't do that if it was still iron. And so then once it scrapes off, it leaves more of the metal exposed, and then more of it can rust, and it just is kind of this ongoing process. So this is a really big problem if you're working with metals. And so here's what happens, and then we'll talk about how we get around that. So oxygen is really easy to reduce in moist conditions, right? So we have oxygen, and if there's water present, it will be reduced, and it will exist as the hydroxide, and this would be a spontaneous process. And if you have acid, it's even easier to reduce. Okay, so oxygen's like, let's reduce all the things, right? And since the reduction potential of most of those metal ions lies below O2 on that table of standard reduction potentials, right? Remember, things that are below whatever we're looking at, they will be oxidized. So most of the metals on the reduction potential table are below oxygen, right? They have, a less positive or a more negative reduction potential. Therefore, they will be oxidized. So oxygen is a really good oxidizing agent. It can, cause lots of things to be oxidized. So here's what happens. And so I'm going to talk through it, but I'm talking about this picture down here at the bottom. And so at the anodic region, the iron, right, and so that's down here, the iron is going to be oxidized to iron 2+, okay? And then those electrons that are being released, right, they're going to travel over to the cathode, right, the cathodic region, and they are going to react with the oxygen, okay? And so then when they react with the oxygen will be reduced. So those iron 2+ ions can be further oxidized to iron 3+, which can then combine with the oxygen that's present, and it can make rust. Okay. In order for all of this to happen, moisture must be present. Water is going to be a reactant in this whole process. And we have to have this ion flow between the cathodic and the anodic regions, right, in order for this to happen. And again, like we said before, if it's acidic, that's going to promote rusting too, because the lowering of that pH was, shown to lower the reduction potential of the oxygen and makes this even more spontaneous. Okay, so in order for something not to rust, we want to keep it away from acids, and we want to keep it really, really dry. We can also prevent corrosion by coating the metal surface to keep it from contacting any corrosive chemicals in the environment, like water or acid or oxygen, right? One of the ways that we can do this is to use paint. I actually worked for a coatings company before I became a teacher, and I worked in a coating that protected, different things. So we protected cars, we protected boats, right? But it was so that it didn't rust. Okay, so different kinds of coatings will help with that. And we can also use different kinds of metals like aluminum. They form an oxide, like when they essentially rust, that will attaches to that metal surface that prevents the rest of the metal from corroding. So it's not like rust where it will peel off and it will expose more of the metal and it will just continue to rust or continue to corrode. This one would just kind of stay on there. Another way to protect our metal is to attach a more reactive metal that's cheap and we don't care about. So like this galvanized nails, right? We have the nail on the inside that we're using is usually made of iron or steel, right? But both of those tend to rust. So what we do is we coat it in zinc, which is more resistant to rusting, and we don't necessarily care if it does, but we'll coat it in zinc. So if it, if the zinc corrodes, then the iron or the steel on the inside is fine because it's going to form an oxide that maybe doesn't flake off. And so we call this a sacrificial electrode because we don't care about what's on the outside because the outside is protecting what's on the inside. We'll also do this with pipes, same kind of thing. We can, coat it with something to protect that iron pipe. And that's it for chapter 19. We've talked about a lot of stuff in this chapter. We learned all about electrochemistry. We talked about voltaic cells. We talked about electrolytic cells. We looked at how electrons flow, redox reactions, how we can do work with those. It's been great. So now you have a lot of practice to do on that chapter 19 lecture worksheet. Make sure you're practicing those problems. Get all of the practice that you need in order to really understand electrochemistry. If you're coming across any questions, please feel free to send them my way. I love to help you out and I love to talk about chemistry. So please, please, please ask your questions if you have them. Otherwise, I will talk to you guys next time.